All right, so today we're going to talk about finding all zeros or roots of our polynomial. We're going to spend a couple days on this, so we're kind of chunking it up a little bit. But there are three important theorems that we're going to talk about today. Okay, and our first one here is called the fundamental theorem of algebra. That sounds pretty important, and it kind of is, but it's actually probably one of the easiest to understand. Okay, it says an nth degree polynomial has exactly n roots or zeros in the set of complex numbers. Which, remember, complex numbers include real and or imaginary, or the ones that are half real, half imaginary. So our complex numbers. So in other words, if we had, say, a question like number 1 here, it says, how many roots does this polynomial have? And our theorem says that if it's an nth degree polynomial, it will have exactly n roots. So because this is a third degree polynomial, right, a cubic polynomial, it will have 3 roots or zeros. Remember, those are kind of synonyms when it talks about roots or zeros. So a fifth degree would have 5. A quadratic, right? Remember, we always got 2 solutions for a quadratic, sometimes a repeated solution, but quadratics have 2 solutions. Linear functions always have 1 solution, etc. So that's important to understand. If I'm solving a 5th degree polynomial, we need to come up with 5 answers. They could be real, they could be imaginary, or they could be complex, where they're half and half. But that's a very important theorem, and that is credited to my boy Gauss, Carl Friedrich Gauss. Okay, our next theorem here, so hopefully that one's pretty easy to understand. The degree tells you how many solutions there are, roots, zeros, solutions. Okay, our second one, called the imaginary complex root theorem, says if a polynomial has an imaginary or complex root, i.e., say 2 plus 3i, maybe this is one of its complex roots, complex number, then its conjugate, 2 minus 3i, must also be a root. So conjugates are things, we saw this when we did, say, the difference of squares, right? Like a plus b and a minus b. These would be called conjugates. I think I mentioned that in our live session. So where the first and last terms are the same, but the only difference is one's plus and one's minus. Okay, those are called conjugates. So in this case, these would be called complex conjugates because they're complex numbers. But in other words, what this theorem is telling us, it says if a polynomial does have an imaginary or complex root, its conjugate also has to be a root. Essentially what this is telling you is that they only come in pairs. If you have an imaginary root, its conjugate is also a root. Otherwise, it's not a polynomial. So our imaginaries or complex roots have to come in these conjugate pairs. So I can't have 1 imaginary root or 3 imaginary roots because they only come in pairs. So we can only have an even number of imaginary roots. Okay, so let's try this out with an example here. It says if negative 3i, which is imaginary, and 5 minus 2i, which is complex, are roots of a polynomial f of x, what other roots must f of x have? Okay, so remember, if it has an imaginary or complex root, then its conjugate must also be a root. Sorry about that. So the conjugate here, so if you think about this as a complex number, this would be like 0 minus 3i. So its conjugate, 0 plus 3i, which we would really just write as plus 3i, must also be a root. So if negative 3i is a root, positive 3i must also be a root. And likewise, for this 5 minus 2i, well, 5 plus 2i, its conjugate must also be a root. So these are the 2 additional roots that we could say here must also be roots of this polynomial f of x. Okay, lastly here, let's combine a couple of these theorems. It says negative 2 is a 0 of this polynomial. Okay, it looks like we have a 4th degree polynomial here with 5 terms, right? Polynomial. List the possible number of real and or complex solutions. Ooh, okay, so this is interesting. Let's see. First thing we can check on, we can use this fundamental theorem back up here. And because it's a fourth degree, we know it has 4 total roots. They could be real, they could be imaginary, it could be a combination of both, right? So we know there should be a total of 4. Okay, well, maybe some are real and or some are complex. So let's figure out, right? Maybe if we have we can maybe set up some columns here, maybe real, imaginary / complex. And then, well, we need to have a total of 4 though. There has to be 4 total according to our fundamental theorem. So let's think about, if my total is 4, could we have 4 reals and no imaginaries? It's totally possible there, right? In fact, and it is given me that -2 is a 0, and that is a real number. Even though it's negative, it's not imaginary, so it's real. So I think maybe we could have 3 other reals and no imaginaries. I think that's a possibility there. 4 reals, no imaginaries, I believe is one possibility. Could we have 3 reals and 1 imaginary to get to 4? In this case, no. And the reason being, remember if we come back to this, the imaginary root theorem says if we do have an imaginary or complex, they only come in pairs. So it is not possible to have 1 imaginary root. So this is not possible. Cannot have an odd number of imaginary or complex roots. They only come in pairs. Okay, well, is it possible to have 2 real and 2 imaginaries? That seems okay, right? We have 1 real sitting here. Maybe we have another real and 2 imaginaries, which came in a pair. So that seems fine. Could we have 1 real and 3 imaginaries? No. Right? Again, I can't have an odd number of imaginaries. They only come in pairs according to our imaginary or complex root theorem. So this is another one that would not work. I didn't give myself much room here, did I? So I think we had one other possibility. What if there are no reals and 4 imaginaries? Sorry, I'm kind of writing at the very bottom here. What about no reals and 4 imaginaries? Now, normally, yes, this would be a possibility. For this particular example, no. Because they told me one of them is -2, which means we have at least 1 real. So in this case, because for this specific example, they told me one of them is the real number -2, we can rule out that case. So our only possibilities is we could have 4 real and 0 imaginary / complex, or we could have 2 real and 2 imaginary / complex. And I think that's it. I think those are our only possibilities here for this polynomial where -2 is one of the given zeros. We have 1 real 0. And remember, imaginaries, these can only come in pairs. That's important. All right, moving to our next theorem. It's our last theorem that we'll need for this section. It's called the factor theorem, at least for day 1, I should say. And the factor theorem is kind of the zero product property backwards, right? I mean, if you remember when we did quadratics and we had something, we'll change this to maybe -3, some quadratic, and we factored it and it was equal to 0, and then we could set each factor equal to 0, right? X plus 2 equals 0, x. And then when we solved them, we end up getting kind of the opposite signs, right? We get -2 and +3 are our 2 solutions. Well, this factor theorem says this is true for all polynomials, but we can go backwards as well. Like if I know -2 is a 0, x plus 2 has to be a factor. And if +3 is a 0 or root, x minus 3 has to be a factor. Okay, so this is kind of what we're getting to with this theorem. Okay, so what it says is if k, some number k, is a 0 or root of our polynomial, or is a root, sorry, that shouldn't say if, apologies there. K is a root or 0 of a polynomial f of x if and only if x minus k is a factor. Okay, so if something is a known root or 0, x minus that value has to be a factor, and vice versa. So if and only if means if x minus k is a factor, k is a 0. Okay, so again, that's kind of like our zero product property backwards. Let's look at some examples. Okay, so let's say if a polynomial has zeros -5, +4, and -1/2, then it must have factors blank. Okay, so remember, if -5 is my 0, x minus -5. So you could think of it this way, x minus -5. But of course, that's going to really turn into x plus 5, right? X plus 5, which is really kind of the opposite sign there. It's the opposite sign of -5. X plus 5 has to be a factor. Okay. Likewise, if I plugged in x minus 4, of course, that's really just x minus 4. We don't need to do much else there. So if +4 is a 0, x minus 4 has to be a factor. Now this next one, you could write this two ways. If -1/2 is a 0, we could say x plus 1/2 or minus -1/2, right? Plus 1/2 has to be a factor. That's true. But typically we don't want to leave fractions in here, because we'll see in some examples that are going to come after this, I might ask you to multiply these together, and I don't want to have to deal with a fraction if we don't have to. Like, give a polynomial where these are zeros in standard form, meaning we'd have to multiply them out. So what we can do is we can multiply this factor by the denominator, by 2. And if you do that, if you multiply a 2 kind of through both parts just in this factor, we're going to get 2x plus 1. So 2x plus 1. And we're not changing the zeros of this polynomial. We're just changing what its equation might look like by multiplying by 2. But now I have a polynomial that would have these 3 zeros. Right? Again, you can think of this one, it still works if you were to set it equal to 0 off to the side, subtract 1 over, and divide by 2. We'd get -1/2 as a 0, right? It's still a factor that gives -1/2 as a 0. So this is it. This is our preferred answer. X plus 1/2 is not technically wrong, but as we're going to see in the next question, most of the time we're going to want to turn it into this kind of nice whole number factor and not leave a fraction. Okay, so our next example, 5, which has 3 questions here, says write a polynomial in standard form. Okay, this is called factored form because it's all factored out. Standard form is when they're all multiplied together and it's kind of descending by the highest degree. So if I wanted to write the one above in standard form, we'd have to multiply all of this stuff out and simplify. Okay, luckily we didn't have to do that for that one, but it is asking us to do that for this next one. Okay, so it needs to be in standard form, and we need to have integer, like positive or negative whole number, coefficients. So no fractions, no using the ones like above. So integer coefficients. Okay, so it's giving us these zeros. So we're going to use our factor theorem. If -6 is a 0, x plus 6 has to be a factor. And if 1/2 is a 0, right, we said we could do x minus 1/2, has to be a factor, but we don't want to leave a fraction. So in the same way we went back and kind of multiplied by 2 in the previous problem, back up here, we're going to multiply this factor by 2 to get rid of our fraction. Again, by 2 because it's what our denominator is. It will turn that fraction into an integer. And so we get 2x minus 2 over 2, or minus 1. Okay, now this is in factored form. To get it into standard form, yeah, we need to multiply it out. So x times 2x is 2x squared. X times -1 is -1x. 6 times 2x is positive 12x. And 6 times -1 is -6. So combine my like terms. we get 2x squared plus 11x minus 6. And there we go. There's a polynomial in standard form with integer coefficients that has those given zeros. Okay. Now, normally, and I tried to make the directions a little shorter, it might say of least degree, meaning don't add in extra zeros, like don't create extra zeros and add them in. But we made these directions as simple as we could here. Okay, for B, it's given me sort of two zeros, so we'll find out. Okay, well, if 3 is a 0, x minus 3 has to be a factor. Let's change colors here. X minus 3 has to be a factor. However, if negative 4i is a root, x minus negative 4i, right? Kind of the opposite sign, x minus k, x minus negative 4i, which would simplify to x plus 4i, right? Minus and negative, has to be a factor. Okay, that's just our factor theorem there. But, I got to go back and remember that complex root theorem says those imaginaries only come in pairs. So if negative 4i is a 0, even though they didn't list it, we have to know positive 4i, its conjugate, has to be a 0 as well. Which means x minus 4i has to be a factor, x minus 4i. Oh goodness, we do have to multiply three things together. But if you want to make your life easier, it helps to focus on the conjugates first. So if we multiply these together, you'll see the middle term will end up canceling out. That's always true with conjugates. So I'm just going to focus on these two first. X times x is x squared. X times negative 4i, it's negative 4xi. 4i times x is positive 4xi. And you'll see those, of course, will cancel out in a second. Multiplying positive 4i and negative 4i, we get negative 16i squared. So combining these, well, the positive and negative 4xi would cancel out. And wait a second, I squared. If I remember some stuff back from our imaginary section, I squared equals negative 1. And we said anytime we see a power of I bigger than 1, we should replace it. So if I replace that with negative 1, we'd get negative 16 times negative 1. Negative 16 times negative 1 ends up turning that into positive 16 at the end. So we're multiplying negative 1 and negative 16. So we end up getting x squared plus 16. That is the term, or the factor, that would get us these two imaginary conjugate roots. Okay, we still have this x minus 3 that we haven't multiplied in, right? We've just only focused on these two so far. So we got to multiply these together. We're almost done. X times x squared is x cubed. X times 16 is 16x. Negative 3 times x squared is negative 3x squared. I know I'm writing this in a weird order just because I knew where everything would kind of go here. Negative 3 times 16 is negative 48. So the last thing you would do is just put them in descending order. I know I kind of oddly wrote them in that descending order already. But this is what we'd look like. This is the polynomial that has those three roots. Okay, our last one is kind of ugly as well, unfortunately. And it's one of the tougher ones when we get a conjugate, a full conjugate, not just an imaginary, right? Or sorry, a complex numbers, not a conjugate. But I guess I did give away, if that is a root, well, 3 minus 2i must also be a root, right? A complex number has to have a conjugate, according to our imaginary or complex root theorem. So, if this is a 0, x minus that quantity, 3 plus 2i, has to be a factor. And likewise over here, x minus 3 minus 2i has to also be a factor. Well, minus needs to be distributed here. It is minus this whole thing. So like adding the opposite, right? We can think of it that way. So in fact, let's even write that like we normally would, adding the opposite. And so we end up with, for this one, x, well, plus negative 3 is just like minus 3 and then minus 2i. Okay, for our other one, we're subtracting again. If we add the opposites, that becomes plus. And so we get x minus 3 plus negative 3 is the same as minus 3 plus 2i. And goodness, now we need to multiply these things together. And what a mess. Maybe the box method of multiplication would work best here. So I don't know. Let me try it out. I don't think I've done this one this way, but maybe it will give me less places to make mistakes. Let's try this box method. Okay, so here's our setup for the box. We're going to put, let's do x minus 3 and minus 2i here. And we'll do x minus 3 and plus 2i here. So this is the second factor I put along this way. And then we're just going to multiply, right? All of our coordinates. So in here goes x times x, which is x squared. In here, remember, I guess everything in this row is getting multiplied by x. So this would become negative 3x and negative 2xi. Okay, everything in this row gets multiplied by negative 3. So negative 3 times the x, right? The x up here is negative 3x. Negative 3 times negative 3 is positive 9. And negative 3 times negative 2i is 6i. Everything in this row gets multiplied by 2i. 2i times x is 2xi. 2i times negative 3 is negative 6i. And 2i times negative 2i is negative 4i squared. Ooh. Which, remember, as we said earlier, if I get an I squared, we got to replace that with negative 1, right? So using this fact back here, I squared is negative 1. And negative 4 times negative 1, this really turns into a positive 4, which we'll be able to combine with, I think, 9, right, is our other constant there. So now we're going to go through and combine like terms and write our answer out here. Okay, so let's see. I've got an x squared. I look in this diagonal, and I've got negative 3x and negative 3x. That's negative 6x. Now, in this diagonal, again, the 9 doesn't combine with our 2xi's, but I do have a positive 2xi and a negative 2xi, which will cancel. And again, remember, a polynomial won't have I in it, so we shouldn't have an I in our final answer. And again, as I go to look, ooh, positive 6i and negative 6i, those cancel each other. That's good. We shouldn't have an I in our answer. And then lastly, our constants, I have a positive 9 and this negative 4i squared, which turned into a positive 4. And 9 plus 4 is 13. And this is the quadratic that has these two imaginary or complex roots. Our last couple examples here. Find all roots given that f of 8 equals 0. So what they're telling me here is they plugged 8 into my function and they got back 0, which means 8 is a 0 / root of our polynomial. Okay, if I plug it in, it gives me back 0. It's a 0 or a root. So they basically gave me one of them. Okay, and in the same way, if I wanted you to break down a number like 143, and I said, find the prime factors. Well, this one would be tough. You could try dividing by 2 or 3 or 5 or 7, like try the prime numbers, and none of them work for a while. This would be tough to break down. But if I gave you a hint, and I said, well, 11 is one of them, what do you think I could do to find my remaining factor? If I kind of gave you that nudge and I said 11 is one of the factors, find the other one. Well, of course, we'd divide. 143 divided by 11 would give me my remaining factor, which is 13. And this idea of kind of giving you a hint or nudging you in the right direction to help break down this polynomial is exactly what they're doing over on the side here. So it's telling me 8 is a 0 or root. So by our factor theorem, I know x minus 8 is a factor right? It has to be a factor. If 8 is a 0, which is what they told me here, x minus 8 has to be a factor. And if that's one of my factors of this polynomial, how can I break down and find all my other factors? We need to divide it out. We'd want to take this polynomial and divide it by x minus 8. And luckily our divisor here is a method where we can use synthetic division. Now remember, we put the 0 of our divisor in the box over here in the corner. And they basically gave me it, right? 8 is the 0 of our divisor. Positive 8 is what would go in the box here. I need a placeholder for x cubed, x squared, all the way down. Whoops, x cubed, x squared, all the way down. So let's set those up down to our constant and plug in our coefficients. 1 in front of our x cubed there, negative 11, positive 14, and 80. No zeros as placeholders necessary this time. Okay, so we set this up. Now remember, because it told me this is a 0, 8 is a 0, and x minus 8 is a factor, we should get a remainder of 0. It should go in perfectly, so that would be a good check for our math here. Okay, so we get this party started. We drop down our 1 times the 8 in the box is 8. Adding, we get negative 3. Negative 3 times the 8 in the box is negative 24. Adding, we get negative 10. Times the 8 in the box is negative 80. And yep, sure enough, we got that nice remainder of 0. So that's my remainder. Remember over here, this would be x to the 0, or the constant, x to the first, and x squared. So the other factor we just found is 1x squared minus 3x minus 10. So this is essentially like we took out one factor, so we know x minus 8 is a factor, and by dividing it, we found our other factor. Now, can we break this down further? It's a quadratic, maybe it factors, right? And in this case, it does. The two numbers that multiply to negative 10 and add up to negative 3 are negative 5 and positive 2. So our quadratic factors further. And if we're trying to find the roots or zeros of this, and we've broken our factors down as far as we can set it equal to 0 and use the zero product property. So if x minus 8 is a factor, 8 is one of my zeros. If x minus 5 is a factor, positive 5 is one of my zeros. And if x plus 2 is a factor, negative 2 is the other 0. And remember, from the fundamental theorem, if this is x cubed, we need to find 3 roots or zeros, whether they're real or imaginary. And in this case, they all end up being real. Positive 8, positive 5, and negative 2. Okay, there's one more down here. I know this video is a little long. Apologies. One more down here. Try this out. Okay, you can pause the video now, see if you can find the rest of the zeros here. Use the example above. Pause the video now and give it a try. All right, this was a tough one towards the end. So if you got to the end, you got your nice remainder of 0, and you properly decoded your other factor. So don't forget to list both of these. The x minus 9, hopefully you divide it out. And this one, this does not factor. There are no factors of 2 that add up to 5. Okay, because this one didn't factor, we need to solve it when we set it equal to 0, like any other quadratic, right? It's just a quadratic, and if I set this equal to 0, we could use the quadratic formula, right? Not a prime candidate for completing the square, because the middle number was not even here. So if you use quadratic formula, x is equal to opposite, right? I do the whole thing. You should end up with, as you can see kind of my steps here, negative 5 plus or minus the square root of 17, all divided by 2. Those are my two. They're real. We actually don't have any imaginary solutions here, right? Because we didn't get a negative number in our square root. They're real, but they're irrational. So like ugly decimals that go on forever and never repeat. So negative 5 plus root 17 over 2, negative 5 minus root 17 over 2, and positive 9. Those are the 3 total zeros this polynomial has. And because they are real, if you were to graph this, it will be crossing the x-axis 3 times. In our previous one, it will be crossing 3 times as well, right, at those 3x values.